imaging with the MKID Exoplanet camera. So Sarah, the floor is yours.
Okay, great. Can everyone hear me?
Yep.
Okay, awesome. So hi, my name is Sarah Steiger, and I'm going to be talking today about high contrast imaging with the MKID Exoplanet camera, or MEC. So first, a quick overview of what I'm going to be talking about. If I could change my slide. There we go. Okay, so first I'm going to tackle the acronym within the acronym, which are microwave kinetic inductance detectors, which are the enabling technology for MEC. Then I'm going to talk about an overview of the MEC instrument with a particular focus on the MKID pipeline, which I had the largest hand in developing. And then finally, I'm going to finish off with an interesting post-processing technique called stochastic speckle discrimination that takes advantage of some of the unique properties of MKID detectors. This is kind of the cheat sheet for microwave kinetic inductance detectors that highlights all of the main properties. So these are superconducting detectors, which are photon counting, energy resolving, and they have no read noise or dark current, and can easily be made into large arrays. And so some of these properties, just looking at them, it's quite obvious why they're useful as astronomical detectors, but I'm going to highlight more of them and explain exactly how we use them in our instrument. So the principle of operation of a microwave kinetic inductance detector, MKID, is that each MKID pixel is a lithograph superconducting resonator, which you can see here. This is on the bottom left here is an actual picture of an MKID resonator, where the area highlighted in blue is our inductor, which is the photosensitive part of our detector. And so you could think of this as effectively a photon variable inductor. And then the capacitor highlighted here in yellow, that we're able to tune. So you can see these legs of this interdigitated capacitor. And we can tune the overlap of these legs in order to give each resonator its unique resonant frequency. And so since we know the resonant frequency of all of our pixels, then when a photon comes in and hits the inductor, it causes a change in that resonant frequency, which we can measure as a change in phase by room temperature readout electronics to not only determine exactly at what time a photon hit our detector, but also by the amount, by the amplitude of that change in phase, we can determine the energy of the photon that hit our detector. So that's on the pixel by pixel level. I mentioned another good property of MKIDs is that they're easily made into large arrays, and that's because of this thing called frequency domain multiplexing. And so we have to operate our detectors at millikelvin temperatures, since these are superconducting detectors. And so kind of a deal breaker is if you have a lot of wiring that you need to bring down to your detector and back out, since you need to cool everything down to, in our case, around 90 millikelvin. And so being able to put a lot of different pixels on a single feed line, a single readout line, is extremely important. Thankfully, MKIDs are naturally suited to this purpose. So since each pixel has its own unique resonant frequency and near perfect transmission off resonance, we could put in a comb of microwave frequency readout tones, which you can see here on the bottom left, and we can read out up to 2,000 pixels on a single microwave feed line. And then down here on the bottom right, this is a picture of a full MKID array. This is a 20 kilopixel MKID array, like the one that is found in MEC. And so we can have a large enough field of view to make these viable astronomical detectors. So where this MKID instrument kind of fits into a broader direct imaging setup. So as many of you know, you have some source. In our case, I'm going to be talking about some bright star with a faint companion. And the light from that source is passing through a turbulent atmosphere, which scatters that light. And so then you need a telescope to extract that light. And in our case, I'm going to be talking about the Subaru telescope. And then you need an adaptive optic system to get that light into as close to diffraction limited PSF as possible, and a coronagraph ideally to block out as much of that light from that central star to be able to image a faint companion as possible. Then you need a science camera to collect that light, and finally a readout pipeline in order to take that information and turn it into calibrated astronomical images on which you can do science. There's kind of a complicating step here as well, in that you can also have the science camera feed back into the adaptive optic system in a process called focal plane wavefront sensing or control. I don't have time to talk about that in this talk, but Christina Davis and Nilay Fruitwala, who are two other members of my group, do a lot of really cool work with that. Since we are a photon counting fast readout detector, we're able to operate at speeds that allow us to do this. So the MKID Exoplanet camera, or MEC, it's an integral field spectrograph, which is located behind Skexio Extreme Adaptive Optic System at the Subaru telescope on Mauna Kea. It operates between 800 and 1400 nanometers, which is J and Y band, as a 1.4 by 1.5 arc second field of view, and contains that 20 kilopixel MKID array that I showed you guys before. It has a hold temperature of 90 millikelvin and an energy resolution R of about 5 at 1100 nanometers. So over here on the right, you can see this is a picture of the silver box here is the MEC cryostat, which is located directly behind the SkexAO optics bench. So now I'm going to talk about the MKID pipeline, and this is how we take those times and phases that we get from the actual MKID detector and turn those into astronomical images from which we can actually do science. So there's a lot here. I'm not going to go through every step, but I'm going to highlight the things that are most unique about an MKID pipeline and as opposed to a standard post-processing pipeline that some of you might be used to. So the first step of processing is that we have all of these firmware generated photon data packets. So MEC doesn't have any intrinsic integration time. We actually count individual photons. And so each photon is its own data packet, which has an associated arrival time and also a phase, which we can later convert into an energy. And so this is written in real time, where we take data for every 1 second of exposure and combine it into one unprocessed file. Next is a cosmic ray rejection. And so this is probably standard in other post-processing pipelines, but the cool thing about our MKID detectors is that we can actually temporally resolve a cosmic ray event. And so you can see that here in this GIF on the bottom. Each frame here is about 2 microseconds. And so we can actually very precisely pick out the exact frames that a cosmic ray happened and remove them from our analysis, only losing on average about 0.01% of an observation due to cosmic ray hits. Next is the wavelength calibration, which is arguably one of the most important steps of our pipeline. And so this is how we take that phase information from the MKID pixel and turn it into an energy for each photon. And we do this by illuminating the array with monochromatic laser light. We usually do about 5 lasers. And then we measure the phase response for each pixel and determine this linear fit over here on the right. And this allows us to find a mapping between phase and energy for each individual pixel in the MKID array. Next is the linearity calibration. So these are resonators, and so you can think of them as every time a photon hits, they ring. And so there's a finite amount of decay time for that phase to get back to its baseline value. And so this institutes a dead time in our firmware that we need to account for that can cause a problem at high count rates. Next is a flat calibration. The difference between our flat calibrations and probably a more standard flat calibration is that ours is wavelength dependent, and so we need to determine what that flat weight is as a function of wavelength. And then finally, you end up with your output files. And so the MKID pipeline can either output FITS files that can be used with standard post-processing techniques like angular differential imaging, ADI, or SDI. You can also output photon time series directly, which is useful for complementary techniques like stochastic speckle discrimination that I'm going to get to in these last couple of minutes that I have. So stochastic speckle discrimination is a post-processing technique that utilizes the microsecond timing resolution of detectors like MKIDs to determine or discern between problematic speckles that are caused by diffracted starlight and the light from a companion. So the idea here is that for a given pixel, the probability of getting some instantaneous intensity is given by this modified Riccian distribution. The main features here that I want you to take note of are these components IC and IS that it depends on. Here, IC is the coherent light component from the star, and IS is the temporally changing component of the boiling speckle field that the companion is embedded in. So here on the right, this is data from a predecessor instrument to MEC called Darkness. And here at these 3 locations, one of them is an injected companion, and the other 2 are just speckles in the image plane. And so by eye, you can't discern which of these is the companion and which is the speckle. But if you plot histograms of the arrival times and fit this modified Riccian distribution, it becomes very clear that this distribution at position A has a qualitatively different shape than at positions B and C. And indeed, it's been shown that looking at this ratio between IC and IS is a pretty good diagnostic to be able to determine between companions and speckles. There is a problem with this technique, however. So you are binning here. In this case, you're using about 20 microsecond bins. And the effectiveness of this technique is quite dependent on bin size. So if your bin size is too small, then you're just going to have like an uncorrelated list of 1s and 0s for whether or not a photon hit during that 20 microseconds or during that whatever time you're sampling. But also at the same time, if your bin size is too large, then you're not going to be adequately sampling the speckle lifetimes, the time scales that the speckles change on. And so this is a problem. And so since MKIDs, however, though, we can get actually the information about the arrival time of each individual photon, we can look at this distribution of inter-arrival times without binning at all in this technique called Binfree SD, where you can fit for IC, IS, and this new component IP, which is just the Poisson component of the companion directly. And so over here, this is the results of running this Binfree SSD on simulated data. Here in panel A, this is the total flux of IP, IC, and IS. And then this is the true components that go into making this image A in C, F, and I. And then panels D, G, and J. These are the results of running this SSD code on this panel A flux image. And so you can clearly see that it picks out the companions quite well. This even does a factor of 2 better than if you performed perfect PSF subtraction, which we can do since this is simulated data, and that is shown here in panel B. So finishing up, since I'm running out of time, some advantages of this method over other post-processing methods is that this doesn't suffer at small angular separations like ADI and SDI do, for example. And also you end up with these IP images, which are these intensity images that can be thought of as theoretically just containing the light from the companion, or containing mostly the light from the companion that can then be fed into other post-processing algorithms to further improve the contrast. So brief plug, so we have a MEC instrument paper that is going to be submitted hopefully this week, so keep an eye out for that. And then there's going to be future work implementing this SSD technique on more realistically simulated MKID data using the MKID Exoplanet direct imaging simulation tool made by Rupert Dodkins in our group that is in the works. So thank you.
Awesome. Thanks so much. Okay, so reminder to put questions in the chat. I see a few people are typing right now, so I will ask my own question. Is it possible that MKIDs could be used to study other like phenomena where you need really good time resolution? Like I'm thinking, for instance, like a KBO occultation or something like that.
Yeah, so we have in the past with one of our previous instruments looked at millisecond pulsars. So for pulsar timing, MKIDs could be really useful. So with MEC, the focus is on exoplanets in particular, but no, they can be used for anything really that you could think of that would require precise timing or low resolution energy spectra.
Cool. Give it a few more seconds for questions. I saw some folks typing.
Yeah, no worries.
So we've got one from David Ciardi. Thank you, Sarah. That was a nice overview of MEC. Sorry if you said this and I missed it, but given that MKIDs track both arrival times and energy, coupled with position on the array, isn't that sufficient to help separate true companions from the speckles?
So you still don't, yeah, so I guess if the energy resolution was better, then you might be able to just from the spectra for an individual pixel be able to determine what is from a companion or a speckle. But since our energy resolution is only about an R of 5, I think that's what prevents us from doing that. That's a good question though. I think.
Okay, we've got one from Max Miller-Blanchard. Great talk. Can you explain a bit more why this technique can do better than perfect PSF subtraction?
That's a good question. I think I would need to look that up and get back to you. Yeah, I don't think I have the answer off the top of my head right now, but I can send you a direct message on the Slack with the link to the paper as well that result is from.
Great. If there are no further questions, let's thank Sarah again for a great talk.